will be covering for sure. So that picture, I'll send you that list. Okay, send me. Please remind me if I don't send you that. Your written assignments. Do you want another assignment? I'm going to give you another assignment in the form of watching videos and commenting on those videos. Okay. Apart from that, do you want a written assignment?
Yes.
What?
A written assignment.
A written assignment
What?
about the next topic.
Yes. Yeah.
Can I make an observation that written assignment, if it can be mostly about this new topic, but if you could also throw in some problems about the first and the second and the third topic, just so we're ready for your final?
Sure, that can be. What I'll do is. So let me make this clear, okay? I'm going to give you one assignment where you can grade yourselves. All right, but I need you to be sincere, because in the past what has happened is, if you write one problem and grade yourself 100%, you're going to get 0. I need you to be sincere with yourselves. Can you do that?
I'm not sure if I understand. I'm not sure if I understand what you mean.
I'll give you an assignment. Okay, you complete that assignment and grade yourself on the effort.
Why wouldn't I give myself 100 for the effort?
If you work on it.
If you put 100% effort on the last day, that does not deserve 100%. You understand?
I don't understand.
So nobody's gonna get 100.
You're saying like have like the integrity, like give yourself the fair grade.
I don't want you to grade. Of course, it's difficult to grade yourself on the effort. I really want you to put the effort so that you get the result. Okay? And what we'll do is we'll solve those problems in class. And then you look at those solutions and then grade yourself.
Oh, that's 100 in the back, so
Huh?
You can't give ourselves some extra credit, bro.
And, huh?
Can we give ourselves some extra credit?
Anthony, unless you do something in the badminton court.
Are you on Wednesday?
Huh?
If I beat you on Wednesday, we don't have to take a final.
If you don't beat me on Wednesday, then
If I don't beat you on Wednesday, then we
and
don't
everybody
have to
else
take
does not take a final, you take a final.
I'm willing to take that risk. So if you beat me, I'm the only one taking the final.
Yeah.
I'm fine with that.
And it'll be, huh?
Hey,
Nobody else takes
I
it.
know what he's gonna say now. I already know what he's gonna say. He's gonna say whatever you make it on everybody's grade.
Wait.
Huh?
You guys want to take that risk?
We don't want to do a final.
He's improved. That's what
And if I beat you, then no one takes the final?
You don't take final for the rest of your course, rest of your program.
We'll see.
If you can beat me.
Okay.
I'm willing to make that wager.
I gotta go see him. And
Alright, make that wager.
if I do good on the next iteration, on the next test in the final.
It's a badminton,
That's gonna show up.
I have to
badminton
get
game.
120.
Oh, bad.
Oh.
Good to go in then.
I suck.
He's actually
You need to help me.
Tori's grade out there.
There's only so much I can
I
do.
don't know. Tori's been getting paid.
Wait, let's let
I
John
just
Bear
gotta-
give us 100 anyway.
I did like
Wait, John.
5 columns yesterday. I did the other. There's 3 more.
Where you seen Mitchell from haircut?
Probably.
Why? But she cut it short.
John.
All right. So what we'll do is we'll skip chapter 5. Okay.
Yeah.
Chapter 5 is about orbit determination. Again, keep in mind what are the orbital elements. there are 6 orbital elements, right?
Right.
Right, ascension,
Eccentricity.
Right. There are three categories, right? The shape and size, orientation, and the position of the orbiting body. Those are the 3 categories. And there are 6 elements, right? Now, we looked at one orbit determination method, right? If you remember, given R and V, because we cannot physically go there and measure these elements. There's a limitation with regards to that, right? Geometrically, what are orbits?
Ellipses. Is that what you're asking for?
That's one of the options.
Circular.
What is a general term for that? A conic section, right? Orbits are conic sections, right? They are 4 conic sections. You studied 4 conic sections as orbits, right? Circle, ellipses,
Hyperbola or not?
yeah, hyperbolas and parabolas. Okay. Now the limitation is we cannot physically measure these conic sections, right? All these conic sections have at least shape and size, the different position of the orbiting body. All those things we cannot measure. So what we do is we devise. There are 2 things which we can definitely measure. Correct? Position and velocity. Sitting here or at a ground station, we can point a laser or a radar, right? And then you can measure the distance, and then if you measure the distance twice, you get the velocity. And you can get the angles as well, right?
Yeah.
Whatever you can do, whatever a cop does to your car to figure out your speed, all that can be done for an orbiting satellite. Okay? Put your cell phones down, guys. Now, this chapter 5 discusses various means of coming up with orbital elements from these various measurements. You understand? Try to understand measurements. This is a very, very key word. How do you do measurements?
Take some sort of scale.
Scale, or what is the general term?
Distance.
Measurements. How do you do measurements? What are those systems which do measurements called?
The
Sensors.
Oh, that.
All these are sensors, right? The lasers, whichever gives you measurement is a sensor or an equipment, okay, or a tool, right? Sensor is a general word. So you can use different types of sensors to do measurements. Can you measure the orbital elements as such?
Yeah.
You cannot measure the orbital elements. That's the limitation. That's what I'm talking about. You cannot measure the semi-major axis. Can you measure the semi-major axis of an orbit? It's going to be very, very challenging. You could do it. You could probably put something on one side of that orbit and another side of orbit, and then try to shine laser lights and do that. But what's going to come in between?
When you just calibrate
Earth is going to come in between, right?
when you just calibrate it though, you can have something that you already have the formula in.
What is calibration?
You said like a standard.
It's a sensor.
What is calibration?
Calibration is when you calibrate it to something else.
What do you calibrate? Do you calibrate measurements?
You calibrate sensors.
No.
You calibrate sensors, right? What do you calibrate sensors against?
Another sensor.
Another sensor, a more accurate sensor, right? So you cannot really calibrate measurements. You can calibrate a sensor, right? So measurements as such, you cannot do measurements, you understand, of the orbital elements. It's going to be very, very challenging. What do? You determine those you mathematically determine or compute those measurements, those elements from the measurements you make. What are the measurements you make? I told you, position and velocity. And this position and velocity, it also covers at different times, right? If you do two position measurements at different times, what do you get? Angle.
Yeah.
Angle and the velocity, okay? So you can do different types of math to determine those orbital elements from those measurements, okay? Now, let's look at orbital maneuvers. Okay. This will be our last chapter for this course, and a very important chapter. You guys know what we just achieved, right? Have you been watching the news?
Inside.
Inside landing, yeah. So it was such a critical. It should be all over the news, and it should be in your thoughts, morning, night, if something like that is happening. It's a very a lot of things have to go right. You see, and why didn't we get that much attention this time?
Where did we get wet? Sorry, I missed that.
There's hardly any attention to that, right?
Yeah.
It's,
We've landed on Mars before.
it is that we have landed Mars, but you remember when Curiosity landed? Yeah. Was there attention?
No.
There's a lot of attention when Curiosity landed, right? What did?
was going through a balloon, right?
There's a lot of attention when the Falcon Heavy launched, but
Yeah, see, Falcon Heavy launched, there was a lot of attention, but this was much more difficult to do. You see, anytime something goes through atmosphere and successfully lands on the surface, it's extremely difficult. Multiple things can go wrong, and you have to keep in mind that after it lands, what is the important aspect?
The
Comes online.
the payload was like safe and secure.
Yes, it has to function, right? Rockets don't have to function. The satellite functions, but the carrier does not function. But here the entire thing has to function. You see, and it has to land correctly, and everything has to work. It has to establish connection. When it is going through, is it communicating? It's probably not communicating because it's sealed, right? And when it lands, then it starts operating, it communicates, it starts sending data. You see, it has to happen now. You cannot miss the date. If you miss the date, what happens? You'll be delayed by several years because you have designed for a certain amount of fuel because it is transitioning, right? And you have to catch it. If you delay, even if you delay by a day, it has gone forward. Now, everything is redesigned, right? You have to accommodate that much more fuel. And you cannot just delay it by a day or a month and say, okay, we'll get there when we get there. You have to make the time, you have to plan for this really in advance and get there and get everything working and start sending data. You understand? This is a really big deal. So what happened? Maneuvers happened. You see? To get there. You remember, you guys attended the presentation, right? The solar probe presentation?
Yeah.
So we always have to do a maneuver when we try to get into another orbit. Okay? So we have to talk about orbital maneuvers. A lot of these smaller satellites, do they do maneuvers?
Maybe.
Yes.
Not a whole lot. Okay? So if you're launching something in the low Earth orbit, you probably don't need a lot of maneuvering to do. Especially the satellites, the student-built satellites or the academic satellites. They are not capable of maneuvering. They get launched and they just keep on orbiting there. You got it?
What about like GPS satellites?
GPS satellites also don't do a whole lot of maneuver. The ISS does a lot of maneuvers. Okay, so think about when do we do a maneuver? GPS satellites, does the orbit change?
No.
It changes. Does the moon's orbit change?
Slightly. But yeah.
What causes an orbit change?
Increase the velocity.
Increase or decrease of velocity or gravitational pull.
That's not going to happen in,
Disturbance.
at least in my and your lifetime. It's not going to happen. Right?
Right.
So if you want to really study what is the more immediate impact of changing an orbit without maneuvering,
Impact on what?
when does the orbit change?
When the speed changes.
Where the velocity changes.
That is true, but that's not what I'm looking for.
What velocity?
Huh? What causes
Are you talking about like the outside force?
External
Other
force.
than
external forces required? Okay.
Okay.
So here, when you are in low Earth orbit, what is the external force?
Gravity.
Gravity and your
Gravity is not external force.
thrust, I guess. That's not external.
Thrust is,
Internal.
it's not external, but it can cause this thing. But there is atmospheric drag. Okay. So whenever there is atmospheric drag, wherever moon is, there is no atmospheric drag. You understand? Wherever GPS satellites are in the geosynchronous orbit. Geosynchronous, not stationary. So stationary means they have to be
No motion.
equatorial. So these are not all equatorial. If it's all equatorial, what happens? US will not get any coverage. So these are geosynchronous. Okay. So they are so far away. There is barely any atmosphere there. Okay. So there is no need for change. They are designed to do that. Once in a while, they might, to avoid any collision or something like that. But what happens with the station?
Used to come back to the
It keeps coming down, okay, because it has huge
size of a football field.
solar arrays, right? So the solar arrays are causing drag, and it is coming down. So you have to keep pushing it up. And plus, there is much higher probability of something striking the station than any other smaller satellite. So when it senses or if there is an indication that there's something is in the way, it's going to move up or down.
Yeah.
Okay. Yes.
so I know. How would you explain Mercury's orbit around the sun? Because that orbit changes without any external forces that I know.
It doesn't change.
But doesn't it? Isn't there? Yeah, it does.
No, the orbits of celestial bodies barely change.
It does. Okay, then I'll have to
Yeah. So that's what
check
is
my research.
you have to understand that Newton's law is a little bit you should let those sink in a little bit more. Okay. So if there is no atmospheric drag, the orbit is not going to change. It's going to change probably over millions of years due to solar pressure or something like that. But for several lifetimes, it's not going to change. Okay? So when you're talking about maneuvers, always keep this in mind. You know, pay attention here, guys, okay? You know this, right? What is this?
It's Newton's.
This is Newton's second law, right? So here, if you expand this, you're going to get m,
Mass times acceleration. Or
right? You
D-
get
dv over dt.
ma, right? But you're also going to get this. You understand? This is basic math, right? I took the derivative of m into v a plus v into d or dt of m. You get it? What you have to understand this, a very, very fundamental, very, very nicely, which one comes first? In nature. No, Newton is not talking about mass. He's talking about two quantities, okay? He's talking about force and
So velocity. So there's
momentum. Momentum, right?
that's momentum. So force.
This is momentum, right?
Yeah, mass times velocity.
MV is momentum. Does change in momentum cause force, or force causes change in momentum?
Force
Force
causes
causes
change.
change.
Force causes change.
It is a state of inertia that determines whether it's this or this.
It's a state of mind.
Inertia.
State of inertia.
State of mind, like, huh?
You know why this is the second law? Because state of inertia is the first law. Law of inertia, right?
Yeah.
What is the law of inertia state?
Object
Stays at rest.
Or at in uniform motion stays in uniform motion, right? So if it's an object at rest, how do you get it in motion?
You apply force.
You apply force.
Right.
You see? How do you what happens if how do you apply a force? You change the momentum. You see? That's how you apply force. How do you apply force?
Change the moment.
How do you apply force on Joshua?
Change the moment.
Change the momentum. So you see, that is the reason you define inertia as the first law, state of inertia. Okay. Now what happens here, you have to understand, force causes change in, what is this?
I have a question.
That's
Off the first one, you implied that momentum's always going down.
No, what is momentum? Momentum is simply defined as this quantity, okay? This is a linear momentum. Mass times velocity. If the momentum changes, what will that result in? Force. How do you change momentum? Apply force. How do you apply force? Change momentum. You see, it goes back and forth, all right?
Okay.
If I take the derivative of this, you're going to get this. You understand? So here, this quantity is very crucial. We often ignore this quantity, right?
Yeah.
In the case of, because we assume that mass will not change. But consider rockets or launch vehicles. Something which is losing mass, right? What does mass loss cause?
acceleration. Or change of force.
You see? This is how you achieve force in orbit. You understand? Typically force, if you look at aircrafts, right? Aircrafts, how do we achieve force?
Or like that. Like,
But what is the principle? Is there mass loss?
Yes,
One
you
word.
Yes.
There is mass loss, but that is not a whole lot. So what is happening is there is equal and opposite reaction. You understand?
Fuel to create thrust.
Because there is thrust being created, and because of that thrust, there is a push being created. Right? There is thrust being created in whatever direction thrust is created.
Yeah.
The thing moves in the opposite direction, right?
Yeah.
But there is nothing like that in a spacecraft. This is what is happening. You see? Mass loss is what is happening. That's the reason thrusters or typical propellers don't work in space. Have you seen any spacecraft with propellers? Why don't they work? There's no atmosphere, right? So here, this is very, very critical. See, change in mass is happening. All right.
That's how vacuum engines work.
Huh?
Is that how a vacuum engine works?
Vacuum measurement.
Yeah, is that how it works? Like how
In vacuum, this is how you create thrust. Okay, when you're maneuvering, you essentially have to lose mass, and the rate at which you can lose mass will determine. Guys, keep your cell phones down. Don't be distracted with your cell phones. Put the cell phone. Kobe, put the cell phone in your bag. Kenneth, put your cell phone in the bag. This is something fundamental. Okay, you need to understand this. All right. So mass loss. Whenever there is mass loss, that will result in force. You understand? Whenever there is mass gain, there is negative thrust. You
So
understand?
mass loss is the only way to create force.
Force in space. Got it? You have to figure out, so that is the reason it's so challenging. So if you want to create mass loss, what do you need to carry?
A lot of mass.
You need to carry a lot of mass, right? And the amount of mass you're going to carry in space is
Minimum
limited. So, and what is it proportional to?
force.
Money.
Oh.
You understand? It is, so mass is equal to money. Every gram, every kilogram you send on a spacecraft will cost you so much to put it in orbit.
What is that? How much? Do you know the number? I
They should have
got
a
the
refuel
number.
station.
It's about $50,000-$100,000 per
Yeah, like astronaut.
kilogram.
You said
So-
1,500. What is that?
$50,000 to $100,000. $50,000 to $100,000. So somewhere in the range of, it depends on where you want to go. Again, if you want,
It's cheaper with the reusable rockets though, right? It's cheaper with the reusable rockets, like with the SpaceX.
there are no, until it becomes a reality, I think it will take some time.
So when it becomes
The reusable rockets I don't think that's going to reduce the cost a whole lot.
Right.
It's the labor that is the most expensive part.
So what do you think the best alternative would be like?
Why do you want an alternative?
So you wouldn't have to spend so much money carrying fuel up. Like let's say like you get an asteroid.
How much do
capsule.
you think a shell of metal tube is going to cost you if you make it reusable? The engine, that is not the most expensive part, right? You see what happened with the shuttle, right? The shuttle was a reusable vehicle, but every time it came down to service it, you know how much they took? They took billions of dollars just to service it and make it ready, send it back again. So until we start, and the amount of investment which has gone through in this reusable vehicle is quite a lot. So to gain that back, we have to launch thousands of satellites. You understand? And that's just a stupid idea to put so many things in space without making sure we know how to get them back, or at least destroy them.
Space junk.
Okay? Yes.
Is there a specific rate that the mass has to change for?
Right, that's what I was going to come to. Okay. So here, this is the first equation
it down right now.
Okay. So here, to answer your question,
Dr. Sunny, what is the
ISP,
ISP? Is that ISP?
right. So here, this relates change in mass to change in velocity. Okay.
That's to the power, correct? That's to the E of the power.
E to the power. This is essentially your rocket equation. Okay. Here, ISP is the
Inertia.
specific impulse of the
The propellant,
propellant, the fuel. Okay. G naught is the
gravitational thing.
gravitational pull or gravitational force at
Where it's launched from, right?
sea level. Okay. And this is the original mass of the system. Right? So here, depending on what kind of delta V you want, you will know this, right? Here, you should understand here what are constants. This is constant, right? Or at least we start. ISP is constant. This is not eccentricity, this is E. Okay? This is not eccentricity, guys. You keep in mind, this is just exponential.
Oh, E is a constant.
But exponential is a constant, okay? ISP is constant for a given fuel. G naught is constant, right? So delta V is directly proportional to delta M.
Is that delta V over ISP? G, is that an exponent?
It's G naught.
It's ISP, no, this ISP is one.
The whole
Specific
thing is
impulse.
Okay.
Okay? So keep in mind,
And what is ISP again?
specific impulse. Impulse, what is specific? Whenever you say specific, what do you divide by mass, right? Specific momentum, specific angular momentum is h, right? Small h. It is capital H over the mass, current mass. Then we talked about specific energy. Everything we are talking about specific in this course. You understand? So here, ISP is thrust divided by sea level weight rate of fuel consumption. Okay. So let me start the discussion for Hohmann transfer and then we can end the discussion here, okay? There are, of course, so why Hohmann transfer? You have to keep in mind, guys, pay attention. This conceptually, this will be a question in your exam. What is Hohmann transfer? And you have to be able to explain it. Okay? Just please pay attention here. It is the most energy efficient two impulse maneuver for transferring between two coplanar circular orbits. Sharing a common focus. There are various aspects I will ask you to explain in this. So just pay attention here. Don't stop writing. Most energy efficient. I may ask you to yes.
When you say coplanar, is that why you got?
I'll talk about it. So most energy efficient. You may be asked to prove that it is the most energy efficient. Okay. Two impulse maneuvers. You may be asked to explain why it's called a two impulse maneuver. You understand? Transferring between two coplanar circular orbits. Coplanar. Sharing a common focus. You see how many concepts are there in this just one statement?
4.
Right? You have to be able to, your understanding until now has to culminate in you guys mathematically, geometrically explaining all of this. You understand? So here, two impulse maneuvers. Try to understand this. When you're in orbit, how do you drive? How do you drive or how do you fly an aircraft? Is it impulse maneuvers? Aircraft?
He said aircraft.
No, right? It is constant, right? It is constant or it is accelerated, right? But it is not an impulse maneuver. For a satellite, if you provide an impulse, so everybody understands this is an orbit, right? Everybody is familiar with that?
Mm-hmm.
You have a orbiting body doing that. Okay? This is the focus. If there is an impulse maneuver, how do you actuate an impulse maneuver, or how do you get an impulse maneuver?
Fire an engine.
Just once. Okay? What is an impulse? Just one, that's an impulse.
Loss of mass.
Okay? So you have one shot of loss of mass. You get it? So if you do that, let's say you do it in this direction. You fire your thrusters in this direction, right?
Mm-hmm.
The satellite is going to change its orbit.
Mm-hmm.
And it's going to be changed. You get it? The orbit is going to change. Only this point is common between the two orbits now. Does that make sense? This was the initial orbit. This is the final orbit. Does that make sense? What did we do here? Impulse maneuver. You don't do constant maneuvers in orbit. If you do that, you'll probably end up. Okay. So what this is, so you understand impulse maneuvers, right?
Mm-hmm.
So in a Hohmann transfer, how many impulse maneuvers are there?
2.
2. You got it? Two coplanar orbits. What does that mean?
They'll be on the same plane.
Same plane in terms of how do you technically communicate that? What is the nomenclature you're going to use for that?
When A dot B cross C equals 0.
That's okay. What is the other?
Can you
Can you ask that
question
again?
like the same?
How do you communicate that with your colleagues who are also space experts? The inclination between these two is
Turn on.
same, right?
Yeah.
The inclination has to be same. Inclination with respect to Earth.
Okay.
You got it? Or the body, central body.
Right.
Both the inclinations have to be the same. Then it's a coplanar orbit. Get it? That is a coplanar orbit. Of course, you understand circular orbits. Right? So this is not a Hohmann transfer. Okay? I'll tell you why this is not a Hohmann transfer. This is just a single impulse plus this is what we are changing is, we're changing from an elliptical orbit to another elliptical orbit. The final part is common focus. When the InSight landing happened, did it happen for the common focus? How do you think InSight landing happened?
Home check.
Is it a Hohmann transfer?
You say that again? I
It
don't
was in
think
orbit,
inside
and went
landing.
retrograde orbit and went down.
What? You looked at the solar probe, right? The Parker solar probe.
Hey man, stop using your phone in class, man.
Nice.
The Parker solar probe goes from Earth to when it is at, it has to first orbit Earth, right?
Yeah.
Mm-hmm.
What is the focus? Earth, right? Earth's center.
Right.
Then it goes to
Sun.
Sun and reduces the velocity and it starts orbiting
Sun.
Sun. What is the focus then?
Sun's
The
core.
Sun. You understand? It's two different foci or two different foci, yeah.
Right.
If you do the InSight lander is not going to go into Mars and just sit there. You understand?
Right.
It has to first orbit Earth
And then it went to.
and then it has to make a maneuver to get closer and then orbit around Mars.
Right.
There it has to reduce its velocity
So like,
and then orbit Mars for some time. Then reduce velocity significantly to land on Mars.
So basically, I said the right.
Huh?
Basically, I said the right thing.
You see? How is the focus changing? First the focus was Earth. Then
Sun.
it became.
it actually will be Sun at some point. Because when it's doing that, Sun becomes the orbit.
Then
Okay? And then Mars.
Okay.
You understand?
the Hohmann transfer to get into Mars.
Right. So that is not a Hohmann. According to this definition, of course, this was applied to two bodies later. But let's focus on this definition first. Okay. So all the Apollo mission was possible because of this.
Right.
Okay. So if you try to understand, you have to read about these. Okay. You have to read about Falcon Heavy. The Falcon Heavy now, what did it launch? The Roadster, right? What orbit is Roadster? What is the focus of the Roadster?
Sun.
Sun orbit. Right? First it was Earth, right?
Yeah.
Everything has to be first put in an Earth orbit. You don't want to carry directly something because then you have to carry a lot of fuel. You understand? You carry only, why is the majority of the fuel required?
To escape Earth orbit.
Earth's orbit, or not escape Earth's orbit, but
Just escape orbit period.
escape Earth's atmosphere.
Atmosphere. Okay.
Once you have escaped Earth's atmosphere,
You can get into it.
you don't need a whole lot of fuel. So that's the reason you see when something is coming back, have we come back from other planets? But have we come back from other celestial bodies?
Yes.
We have come back from? Why was it so easy, possible to do that? There is no atmosphere, right? So we didn't need as much fuel to come back.
Can we go back for a second? On the third point, you talking about two coplanar circular orbits.
Hmm.
You just saying that the inclination are the same?
Right. Inclination is always measured with respect to this Earth's, this thing, okay? The central body. The central body, the inclination of these two has to be the same.
Okay.
You understand? That is what means coplanar. Otherwise, if the inclination changes, what happens? There are different planes, right? Okay.
Also, you didn't go over why it was the most energy efficient.
We'll mathematically prove that.
Okay.
Yes.
So basically what you're saying is, before I can do a Hohmann transfer, I need to make sure my planes are the same.
If you do a Hohmann transfer, your planes will be the same.
Okay, but that's the step before the Hohmann transfer, matching the planes?
There is no second plane until you do a Hohmann transfer,
Okay,
right?
so I couldn't do it without.
It's all space before you do the Hohmann transfer. If you do a Hohmann transfer, you will be in another plane. If you don't get into the same plane, what did you do? You did a non-Hohmann transfer. Hohmann transfer will result in coplanar orbit. Okay. All right.